So we have Ekaterina from EPFL. She is in her third year of the PhD, working with Professor Michael Caprolo. She is broadly interested in applying theoretical insights to machine learning and make algorithms. Yes. Yeah.
Great. Hi, everyone. Today, I would like to talk to you about our approach to scheme and attention approximation, which recently turned into a NeurIPS paper. And if you would like to discuss it in more generality afterwards, I'm happy to do so, or you can also find it in arXiv. Let me first briefly cover the basics. For the purposes of this talk and the paper itself, a transformer-based model is processing the input and the question to the input represented by tokens. Every token corresponds to 3 vectors called key, query, and value embeddings. And during the generation phase, we compute a function called attention, which takes a current token, everything in the past, and formally defined as the expectation of the value vectors from the past over the softmax distribution. What this is doesn't really matter right now. We will cover it later. Now, clearly, in order to compute attention exactly at every time step, we would have to keep everything, which is maybe suboptimal, and several prior works dealt with this problem in different ways. 2 broad approaches to this problem are quantization, which amounts to storing the vectors, all its vectors, but not exactly, in some lower precision format, and token pruning, which is a method which only selects some of the tokens, most important tokens, and discards the rest. Our method, called BalanceKV, is an example of a token pruning algorithm. Now, the conceptual contributions of BalanceKV is that it is, first of all, a provable algorithm, and second, it is question independent, which means that in order to compress the prompt, we never have to look at the question itself. This is the properties that other works don't have. All of them are purely heuristic. In the remainder of the talk, I will explain to you what BalanceKV is and roughly why it works well. At the end, I will present formal guarantees and then move on to the experimental section. And just before we get into the problem that we're solving, I will quickly remind you the formula of attention, although probably everyone knows it. In the numerator, we have a linear combination of value vectors of the past with exponential coefficients, and denominator just serves to normalize those coefficients so that they sum up to 1. For us, however, it will be very important that attention consists of a numerator and a denominator, as we will treat them separately from each other. More precisely, we denote our key cache as K, our value cache as V, and we just bound ourselves to a very simple task of compressing the key cache K by a factor of 2 into a set called K2, which we will then use to approximate the denominator. Separately, completely, we compress K and V by a factor of 2 to get sets K1 and V1, and use them to approximate the numerator. Crucially, the query is not known to us in this process. Formally, query is defined arbitrarily before we start the compression process. Afterwards, it's revealed to us, and then, with high probability, what we have built should work well to approximate attention. I am intentionally very vague of what it means to approximate attention or what it means to work with high probability. All of that will be clear in the part of the talk dedicated to theoretical guarantees. For now, for simplicity, everything is very vague. And right, we have to deal with numerator, denominator, but there is a very simple algorithm that does this. We could just sample half of the data set for the numerator, same for the denominator. That's a beautiful algorithm. You can even prove theoretical guarantees about it if you would like. but obviously it works worse than BalanceKV, otherwise I wouldn't be here. And the reason why is because uniform sampling doesn't know anything about keys and values. It's just sampling some indices and using whatever we got to approximate attention. That's the key reason why BalanceKV performs better, but more on that later. Right. We have to approximate denominator and numerator. Let's start with a simpler task. Approximating the denominator. There's no trick about using the estimator. It will be the same as for uniform sampling. The whole essence of our algorithm is in how we choose K2. And I would like to present to you a very simple observation, but very important to us. It is actually the same task to approximate denominator of attention as on the screen and to balance the denominator. By balancing the denominator, I mean selecting signs for each of the terms without knowledge of query so that the entire sum is roughly 0. This concept can be easily illustrated with a picture. In this picture, the black box represents our entire denominator. The circle B represents the summons of our approximator, and A is everything else. And now, if it so happened that 2B is roughly A plus B, then A is roughly B, or equivalently, we can give pluses to set A, minuses to set B, and the entire signed sum is roughly 0. This allows us to view our problem as a balancing problem, just to iterate. And a very similar framework has been known before in discrepancy theory. There's something called a vector balancing problem, which also assigns signs to vectors UIs without knowledge of direction Z. And the goal of vector balancing problem is for the signs to be such that the sign sum is small in unknown direction Z. It is not very difficult to see that our goal is a special instance of vector balancing problem. We can design a mapping into a high-dimensional Hilbert space, which will map the vectors, the key and query vectors, so that in this Hilbert space, the inner product is precisely the exponential in the screen. Just to formalize it a bit, there exists a mapping phi with the following properties, and plugging the phi of k into ui's, phi of q into z's, maps our problem precisely to the vector balancing problem.
It's kernelization.
More or less, yes. Well, yeah, it is a kernel method. Now, this interpretation of our problem allows us to forget for a second about attentions and just task ourselves with solving the vector balancing problem. We will restrict ourselves to finding an algorithm which processes vectors ui, un one by one, determines the size also one by one, so that all of the intermediate sums are small. This will be our guarantee for why the end sum will also be small. Crucially, I would like to underscore just one more time that Z is unknown to us. But in order to at least get some sense of how to solve this problem and what we can get on the right-hand side, how small is small, let's assume that Z is known for a second. In that case, I will even go even further. Suppose you only have 5 vectors and all of the inner products are given to you. In this setting, our problem is just a number balancing problem. Our task is to determine signs 1 by 1 so that everything in between is small. Now, I would like your help on this one. What do you think should be the first sign for the one? What's your favorite?
doesn't matter, I guess.
Yeah, it doesn't matter, you're right. But my slide says it's plus, and it's plus. Now, yeah, so the problem of selecting the second sign, unfortunately, is harder than the first sign. Should it be plus? Should it be minus? And why? All right, I'll tell you. It's a minus, and that's because if we select minus, our intermediate sum is closer to the zero, as opposed to if we select plus. Now, like the whole principle, I guess, is clear. The third sum should be again a plus because our current subsum is negative. But if we move on to sum number 4, it becomes positive here. And in order to balance vectors better, we have to select minus 4 u5. Now, this can be turned into a theorem. Well, not a very inspiring one, but still, if I were to give you an infinite or a very long stream of these ui's, and if I were to promise you that all of the inner products are always bounded by 1, then with an extension of this algorithm, you would be able to keep all of the intermediate sums bounded by 1. Just because if you have something positive right now, you select minus, and the other way around. Even though this doesn't seem like a lot, this is actually this algorithm gives us a very non-trivial conceptual contribution, because if you were to instead select signs uniformly at random, then if all of your, say, inner products were exactly 1, and by some Chebyshev analysis, your sum would be on the order of square root of n. Turns out that this result, or a very similar result, applies to the setting where z is not known. And this follows from a beautiful result by Banachek. More specifically, if I now give you vectors of length at most 1, there exists, you can sample a Hahnian function sigma from some unknown for the moment distribution p, so that for any given direction z, your sign sum is in projection to z gives you something on the order of logarithm with high probability. Now, you could object and say, well, just existence of this distribution doesn't say much, but sampling from this distribution is also trivial. And the algorithm is very similar to what we built in our toy example. Just like before, we process vectors u1, un 1 by 1. And at every time step, we are more likely to select a plus for a vector if it's anti-correlated with the sign sum of the past. And we are more likely to select a minus if it is correlated. That way, we ensure that our sum of the vectors does not grow indefinitely and concentrate somewhere around 0. And just to finish the conversation about approximating the denominator, all of this theory we developed for the problem of attention approximation, let's plug in our mappings of key and query vectors into the algorithm. The final algorithm that we use in our paper for approximating of denominators is on the screen right now. Now we move on to the numerator, and I promised you the algorithm for approximating the numerator will be quite similar to what we just saw. Let's just quickly recap the problem that we're setting to refresh our memories. Attention, the formula for attention is on the screen. In the prior part of the talk, we learned how to compress the key cache by a factor of 2 so that we get a good approximation to the numerator with the following formula. And right now, we would like to do something very similar, but for the numerator. And the function that we would like to use for approximation of the numerator, again, is the same as if you were to sample half of terms from the numerator and use that in order to approximate it. Similar to before, our problem is equivalent to the problem of balancing terms of the numerator. And just like before, we would like to use the vector balancing problem framework in order to solve it. Except that now the embeddings that we will use are a bit more involved than before. Remember that in order to connect the two problems, we have to build an embedding of keys and vectors so that the inner product of these vectors in some Hilbert space gives you precisely the vector balancing problem. But the vector balancing problem balances numbers, and we would like to balance a vector so that it stays close to 0. You can show that embedding C works for our purposes. Let's just quickly plug it into our self-balancing walk algorithm to get the final thing for our problem. I think I will skip the proof sketch of why embedding C works well for us, but if you would like to talk to me about this afterwards, I'm more than happy to let you know roughly how the performance guarantees work out. And
There's a question.
oh, okay, sorry.
Yeah.
Hi, maybe I missed something from the beginning. Is there any specific reason why you want to do things sequentially? This sampling is sequential. Is the reason why you take this log n factors because you are sequentially doing things, right?
The reason why log n appears is because the query is unknown to us. And
But why do you want to do things sequentially? Why is it the case that P sub j only depends on the past realizations and not the future ones?
well, I guess we task ourselves with the KV cache compression for tensor-based model, and as far as I know, there the attention is causal. It's only applying to the past. If I understand your question correctly.
Yeah. My question is exactly why are you essentially tied to this sequential algorithm? Is it inherent to the problem? That's the part that I might have missed from the beginning of your speech. Is it the sequential nature of the problem? Is the nature of the problem sequential, or is it more like you are using this sequential sampling scheme to solve the problem, which may not be sequential in nature?
I would guess that the problem of KV cache compression, especially in the streaming setting, is sequential because your past keeps on growing, and you would like to keep your KV cache small for each of the generation steps. But as a theoretical question, I think it was just inspired by ML and by memories of transformers.
All right. Thank you.
Thank
Makes
you.
sense. Thank you.
And in the last part of the theory segment of my talk, I would like to very briefly cover the theoretical guarantees of BalanceKV and application to streaming. Just to refresh, the problem that we were solving was quite trivial. We only wanted to compress our KV cache by a factor of 2. If the problem was in the offline setting, we could simply iterate our algorithm independently on the numerator and the denominator and compress it for as long as we like, or for as long as the errors don't accumulate too much from the compression. The streaming application of this algorithm is quite standard. There is a technique known as merge reduce, which amounts to, or there's a family of techniques of this sort, which amounts to batching up your stream and planting a binary tree on top of it, so that in each of the mini batches, you only compress your input by a factor of 2, but then in every node, as soon as the offsprings were compressed, the higher node collects everything remaining and compresses it more. This indeed can be implemented in online fashion, in case if anyone wanted to implement it. Moving on to theoretical guarantees. I can give them to you, we should first formalize the problem that we are solving. We say that a vector approximates attention well if the alto norm of the distance between attention and this vector is small. And how small is small? It should be small in terms of some precision parameter epsilon and functions of the value vectors and key vectors. That is softmax and Frobenius norm of the matrix of value vectors. It turns out that under this problem definition, the size of the best core set that uniform sampling can give you is on the order of 1 over epsilon squared, whereas BalanceKV can compress the data set all the way down to something on the order of 1 over epsilon. And seeing these numbers, it is natural to ask ourselves if we can do anything better than what BalanceKV and uniform sampling does. And we take a step towards resolving this question by providing a lower bound on the streaming space complexity of attention approximation. Specifically, we show that under this definition of epsilon approximation, any algorithm that does it has to have space complexity of at least 1 over epsilon squared or d. While it is true that this lower bound does not match the performance of BalanceKV or uniform sampling, still it opens the door for future explorations. And well, at least I think that's an interesting problem to resolve, to close the gap between the algorithms we know and the lower bound. Now, are there any questions about this so far?
So for your definition of attention approximation, like epsilon larger than 1 over square root n doesn't really make sense, right? Because
Right.
our values are, I mean, the Frobenius norm of the value matrix is pretty large compared to the vector, which is very small.
I guess it depends on what the value vectors are, right? If there's only one,
I mean, usually you assume that all of them are sort of
right?
unit vectors or maybe similarly looking. So the Frobenius norm of V grows as square root n with the number of vectors you have, but the attention output is usually like some constant length vector.
Right. I think epsilon, it makes sense to consider epsilon as maybe a constant or some function of d for the theoretical setting, but then in practice, of course, everything is different. We need to look at the experiments separately.
Yeah, then the uniform sampling is basically telling you to sample everything, right? If you have d over epsilon squared, then that's all of them. BalanceKV at least gives reduction. Yeah.
I think this is it for the theory part. But the theory part basically told us that it does make sense for our algorithm to use the geometric properties of keys and values. Well, at least theoretically, but let's see if that's also true in practice. We perform all of our experiments on the open source weights models Llama and Quen. And the first experiment I would like to show you is exactly the implementation of our theoretical problem. We take a data set of long bench trivia QA. We take Llama as our model. We select a few of different layers of Llama. And then we take BalanceKV and uniform sampling and apply both of them in order to compress prompts by the same factor. More specifically, in this plot, we see compression by rates 2, 4, 8, and 16. And as it turns out, BalanceKV always performs better than uniform sampling, even in the regime of constant error, which means that there is something happening on real-life data which we can't even really explain by our theory, because theory suggests uniform sampling can perform better. Now, a very similar effect is observed in all of our end-to-end experiments, which are experiments on long bench and needle in the haystack. In our experiments on long bench, we use BalanceKV, uniform sampling, together with all of the state-of-the-art heuristic algorithms like SnapKV and PyramidKV, and apply all of them to the data sets in long bench in order to compress problems by a factor of 4. In the slide, you can see the average scores across the methods on 3 models, llama and 2 variations of quad. And as you can see, BalanceKV performs comparably or better than the state-of-the-art heuristic algorithms, and it outperforms uniform sampling. For needle in the haystack, things are a bit different. Needle in the haystack in its nature is a problem of retaining some very important information in the context, which BalanceKV, being a probabilistic algorithm, doesn't do as well. If you remember, the first thing BalanceKV does is separating the data set into 2 parts and keeping one of these 2 parts. And to be honest, the way it selects which part to keep is random, because there is no way we can tell which of the 2 parts is better. So each of your important tokens are dropped at least with a probability 1/2, which is not great. So instead, we take our method, we take a heuristic that picks out a couple or a few of surprising tokens from the prompt, and then uses the compressed cache by BalanceKV, these surprising tokens, and then in the combination of that, we apply to needle in the haystack. The subroutine which picks out the surprising tokens is very simple. We just look at our key embeddings and we basically pick out all of the tokens for which the key is perpendicular to all the other keys, which, at least intuitively, it seems like that's a surprising token and you should keep it. And as you can see, with this heuristic, BalanceKV still performs better than uniform sampling, which means that, at least intuitively, just preserving the needle with our heuristic is not enough to give a perfect algorithm for recovering the needle in the haystack. There's still some information in the context, and it is still important to compress it well, and BalanceKV still does it better than uniform sampling. Final notes at the end of this presentation are the future directions, which I think might be interesting. The first one, I won't really discuss it any further. It's the theoretical problem of closing the gap between our lower bound for space complexity of streaming attention approximation problem. The second bullet point is the following. So our algorithm is engineered. There's nothing learned about it. It's at most it's probabilistic, but it does show us that there's something in the data which is well captured by BalanceKV and which we don't completely understand ourselves. For example, the setting of constant error epsilon is not really explained by the theory we have. So maybe it makes sense to, instead of manually minimize discrepancy with a self-balancing walk, to instead learn the way to optimize discrepancy via a neural net with a couple of layers. A more broad thought on the topic is the following. See that the way BalanceKV managed to, the way we're able to apply BalanceKV to the problem of attention approximation is by viewing the problem of approximating this function as a balancing problem. Now, there's not only attention in a transformer-based model, there's also feed-forward layers, which are also functions of a bit different sort. Maybe it would be possible to view the problem of approximating that function as the problem of finding discrepancy of components that go into it, and then extend the notion of discrepancy to the transformer as a whole and minimize that. At the end of the day, attention only constitutes, as far as I know, like 30% of the memory of a transformer. So studying discrepancy of a transformer as a whole is an interesting direction and would be much more beneficial. This is all I wanted to tell you today. And if you would like to ask any questions about anything, I'm happy to discuss them.
Thank you. I
So,
had a question about the how well it aligns with the flash attention and some other efficient implementation metrics that also do not really need n-square memory, because they just by the fact of chunk processing, they can already be, say, linear in memory.
Right. I guess this works well during prefill, but not
Yes,
necessarily during generation.
Mhm.
So, right, in all our experiments, we don't compress the like we do prefill as is with flash attention,
Mhm.
and in parallel with that, we compress the KV cache, which we then drag along the way during the generation stage.
so you use the same algorithm as you generate tokens? Do you assign plus or minus to the newly generated key or value and throw those away, or do you keep all the newly generated tokens?
Yes, we keep all of the newly generated tokens as is for long bench because there the size of the generation is much smaller than the context. But yeah, it would be an interesting task to. We have a streaming algorithm in this paper where we never implement streaming in our experiments because that's not needed. But
I mean, yeah, there are long generations now as well with the thinking models and so on. So
Particularly for a rail, perhaps it might be interesting.
if there are no more questions, we can end the talk, I guess.
yes,
Thanks a
Thank
lot
you.
for giving the talk.
Thank you.